So I'll start the material, okay? So so far, since the beginning of the class, so it's been like 2 weeks now. So far, we have been talking about different structural systems that are subjected to stationary loads, okay? Whether it's a point load, whether it's a distributed load, or what kind of incline load. So those were stationary, right? So today we are going to talk about the moving loads. So for example, what happens if a car is moving across a bridge? So what happens to those reactions? What happened to the moments, shear? What happens to those, actions? Basically, what I'm saying is the variation of those actions. So this will be actually handled. It's called the influence lines. So that we will be looking at the influence by moving a load across a span or maybe a continuous member, and then see what happens to those reactions or actions or moments or shear, right? So we will be talking about two different methods that can handle the influence lines. One is the tabular method, right? And the other one is very easy, straightforward. You just look at the structural system and then you draw it, using your hand. So it's called the Mueller-Breslau method. So basically what we will be doing is that using these two methods, we will try to construct these influence lines. And of course, we will be doing some in-class examples. So in these examples, I will be covering beams, and unit loads, beams with uniformly distributed loads, right? It's moving, keep that in mind. And also I'll be talking about the trusses as well. So everything that is applied onto a structural system, now they are moving. They are no longer stationary loadings, okay? All right, so now let's look at what influence line. So if you can see in this slide, you can see there's a bridge system, okay? Bridge here connecting three different spans from A, C, CE, and EF, right? So this bridge is supported by continuous members or columns, one at A, one at B. There's a hinge at C. There's another column or pier at D, and there's another hinge here, and there's another support or pier. So if there are traffic on top of this member, right? Let's say this vehicle is moving from A to F. These reactions, for example, the support reactions or the moments in between these spans or the shear, they will not be stagnant or they will not be stationary, because these actions are dependent on the load, where the load is applied, or it is called as location dependent. So for example, if our car is on top of A, the reaction of this RA will be very, very high, or maybe it is the same as the weight of this car, right? But if you measure the reactions of these supports, they do not have any reactions because it's right on top of A. But if you just push a little bit further up, then now B is starting to feel some reaction, right? And also there will be some moments, there will be shear, and a lot of things are happening. So the importance of using an influence line diagram is that, for example, if a designer wants to design some support, so as the vehicle is moving from A to F, he needs to know that what is the maximum influence on this support reaction happens at what location, for example, because without knowing the location, you cannot see the reactions, right? So you need to place different locations, this load, and see how these reactions are going to change, right? So the basic idea of an influence line is that you place a unit load. Let's say this is a one kip, okay? Just pretend that this is one kip, and then you move along a certain a member, right? Let's say this is a girder, and then see the variation of these reactions. That is in terms of reactions. Of course, we have internal loading such as moments and shear. So we are interested in some particular location, right? So the overall idea is that we are trying to develop, or we are trying to draw something that tells us the maximum influence on a particular location or a cross section of a beam. Okay, so let's go to the next slide. So the influence line, this is the definition of what an influence line is. So influence line depicts the variation of a reaction, right? Internal shear, internal moment at a specific location. So we are interested in a specific location on a structural element, okay? And this on this structural element, this load is moving from one end to the other, right? And this moving load is represented by a 1 unit load. Again, I'm saying that this could be 1 kip, 1 kilonewton, 1 newton, 1 pound. So it should be 1 unit load. Okay. So for example, if you think about this member AB is a simply supported beam. So of course, at A, we have reactions, so vertical reaction and horizontal reaction. At B, there is vertical reaction because of the roller support. Now, if I move this 1 unit load, let's say 1 kip or 1 unit. So if I move from A to B, how does the reaction at A changes as the unit load travels from A to B? So that is one concern that we have, because depending on where this load is located on top of this AB beam, your reactions is going to change, right? Because it's location dependent. The load is the reactions are load location dependent. Again, what or how does the shear at C, for example, C is somewhere in the middle of the member, okay? So this is called internal shear at this location, right? So how does the shear at C change as the unit load is moving from A to B? By intuition, you know that from when you have on top of A, shear is going to be 0 because all the load is taken by this support. But if you push this car a little bit ahead of the support A, then the C location or C cross section of that material, let's say this is a concrete girder, in that particular cross section will start to feel these internal loadings, right? And again, there is another influence here coming from the moment. So how does the moment at C, so this is a particular or specific location. See, this is, I have highlighted here. So we are interested in specific location, and action is now the moment. We are interested in the moment about C, when this unit load is moving from A to B. So we have 3 different actions. One is the support reactions. The other one is the shear, internal shear of a member, right? And the other one is an internal moment. So depending on which action type we are interested in, we will have 3 different influence line diagrams, right? So the distribution or the variation of an influence of the action, for example, the reaction or the shear or the moment, is represented by the influence line diagram, right? So we have 3 different actions for reaction, shear, and moment. The way that we will be using, or the method that we will be using, will be based on 2 different methods. right, to construct this influence line diagram. One is the tabular method. So the tabular method is essentially saying that we apply or place the moving load at different locations and use the static equilibrium to compute the reactions, the shear, and the moment at a required location, right? So similar thing that we have discussed over here is reflected on this tabular method, right? So essentially what we are doing is we will place a moving load, let's say this is A, right? And then we will place at different location and then see the effect or the influence at a particular location on the beam. And the variation will give us the influence line diagram, right? The second method is called the Mueller-Breslau method. So the Mueller is probably, if I'm not wrong, he's a German civil engineer. So he came up with a fictitious method to qualitatively determine, but it has no values in it. But the shape of the diagram, he just looked at the structure or structural system that we have, and then by just looking at the structural system, he came up with a way that you can draw the influence line, the shape of the influence line. So we will also talk about that one in detail after we complete this tabular method. Okay. Any questions so far? I believe no. It's pretty clear. No questions? And also on this over here, this is the positive sign convention that we have already, got used to. So if you consider the left-hand side of a structural system, the cut, downward shear is positive. The axial load to the right is positive. Counterclockwise moments are positive. And everything is reversed on the right-hand side of the cut. Upward shear is positive. Clockwise moment is positive. And the axial load to the left is positive. So the positive sign convention will be carried over in this lecture as well. Let's take a look at the support reactions first. Okay, so in this one, we have a beam that is supported at A and B. At A we have a pin support, B we have a roller support, and then we let this 1 kilonewton or 1 unit load moved across this span from A to B. So we are interested in plotting the reaction influence, right? Plotting the reaction influence line for the support reactions at A and B. So by virtue of it saying reaction influence, that is reflected on the supports, okay? So we have two supports. The question is that how does this support A and how does this support B changes, or the reaction changes when you move this load from A to B. So we will be using the tabular method. Okay. Now, if you remember the tabular method, it says we need to apply the unit load at different locations along the beam, and then we need to compute the reactions for A and B separately. Okay. It's being recorded. Yes, correct. Okay. All right. So now let's look at the beam itself. Now what I'm going to do is we place this unit load, right, at A, because that's the place where we're going to start. Otherwise, in other words, let's say X equals to 0. So X is measured from A. When X is equals to 0, my unit load will be on top of A, right? So, and now we will be using static equilibrium to find out the reactions at A and at B. Since our unit load is at right on top of A, that means my reaction at A is the same. It is going the opposite, right? And on the other hand, my reaction at B is going to be 0 because that's how this system is in equilibrium. Also, you can see that if you take the moment at A, right, and see the moment equilibrium, so RB times whatever this length, let's say L, right, RBL is equal to 0 because there are no other applied loads across this span. So therefore, my RB, or the reaction at B, is 0. Okay, and what happens if I move further this unit load? So let's say I am at the mid span now. So now see the difference here. So when I move this load from A to the mid span, see the reaction is changing because now it is in the mid span, and then the supports are sharing this load equally, right? So this is one unit load. So this will be 0.5 and this will be 0.5. Okay. And next, when I move further up, and let's say I place my unit load on top of B, what happens is my reaction at B is going to be 1. My reaction at A is going to be 0 because I don't see any reactions because this load is right on top of B. Now you saw that depending on where we place this unit load across the beam, my reactions are changing. Okay. Now let's see. We can plot this one depending on the location that we place our load on the member AB, right? So let's say I have placed 3 different locations. One at x equals to 0. The other one is at x equals to L over 2. The third one is x equals to L. So depending on these locations, I have found out the reactions at A and B, right? So 1.50 for support A and 0.5 and 1 for support B. Now we can plot variation of the support A. For example, when x equals to 0, support A is 1. When x equals to 0, support A is 1. When it is x equals to L over 2, where it's in the midspan, that will be half of that. And when the x equals to L, my reaction at A is going to be 0. It's just a straight line that is going from 1 to 0. So this is called the influence line for the support reaction A, because now this is the representation of the variation of the support reaction at A. And similarly, you can get the reaction, the support reaction B, the variation of support reaction B, by plotting the 0 and 0 over here, L over 2 and 0.5, L over 2 and 0.5, L and 1, L and 1. So these two diagrams are called as the influence lines for the supports at A and support at B when you move the unit load across A to B. Okay. So what happens now? Maybe I'll ask a question and then think to yourself. Okay, what happens if I put 10 kilonewtons of load here? Now this is a unit load, right? If I put 10 kilonewtons on top of this and then let it run from A to B, what will these values be? These values will be scaled up by 10 times because the thing is we ran this moving load considering that this magnitude is 1 unit load, right? If we have 10 kilonewtons, then this 1 is multiplied by 10 kilonewtons, right? So all of them will be in now kilonewtons and also multiplied by 10 because we are moving a 10 kilonewton concentrated load from A to B. Therefore, my influence line diagram will only multiply by this axis, okay, multiply by 10 kilonewtons, or otherwise you can say it will be scaled up by 10 kilonewtons. But essentially the shape of the diagram will be the same because it's just a matter of scaling up by a constant, right? So this is what I said. What if the moving load was 10 kilonewtons? If it was 100 kilonewtons, you just multiply by 100. Second one is the shear, right? So if you can remember, right, shear force diagram, so you have high shear at the supports, and then when you move into the member, your shear is decreasing, right? So now this time we are looking at the shear influence line. Earlier we talked about the support reaction. Now we are looking at the shear influence line. So the shear is calculated somewhere in between the member, right? For example, this is a simply supported beam, and there is one unit load is passing through from A to B, and now we are interested in calculating, or we are interested in looking at the influence of the shear at point C. So this point C is 2.5 feet away from support A, right? And then we are using the tabular method. So what we need to do is we need to place at different locations to see how the shear at C is going to change by using equilibrium equation or static equilibrium. Let's look at this. So this is the same AB simply supported beam, okay? So I place my load on top of A. If I put my excuse me. So if I put my unit load on top of A, my reaction is going to be 1 because unit load is 1, reaction is 1, and over here this is this reaction is 0. Now what happens if I move from here to C? For example, no, before that, let me just see the shear here. Now we have found out the reactions here, okay? So the next thing is to look at the shear because that's what we are interested in. So what do you do if you are interested in shear in a member? So you take a cut, right? So you take a cut at point C and see the equilibrium. Now let's see the equilibrium here. So this is the cut. So this is C. This is the place that we are interested in looking at the shear, okay? This is the support reaction that we found out from the previous step by enforcing the equilibrium equations. And this is the original location of our unit load, okay? So now we have forces. So if you can remember, this is the left cut of the member. So therefore we say downward shear is positive. Let's consider that as VC. So VC is basically given by the shear or the shear force at C. Okay. So VC is positive because it's going downward. Plus 1 is this force, the moving load. Now at this time, we have this moving load on top of A. So it's giving me a positive shear. And this is the reaction coming from the equilibrium, okay? So that is a negative shear. So this is equals to 0 because this piece needs to be in equilibrium. So if you consider the shear at C, shear is the net shear at this cross section is going to be 0. Okay, so that is one thing that we need to know. So if I place my load here, the shear at C is 0. Otherwise, not otherwise. In other words, when x equals to 0, my shear at C is 0. That's one data point, okay? So now I'm gonna move my force along the beam, right? So if I have, or if I place my load on C, now what happens? My reaction is going to change at A. My reaction is going to change at B. So how do you get this? So this is 1. So this distance from here to here is 2.5. And therefore, this distance will be 7.5. Why? Because AB is a simply supported beam with a span length of 10 feet. Okay? So you know the distances from here to here, distance you know, from here to here you know the distance. You know the load, which is 1, and RA will take a proportion of this 1, RB take a proportion of this 1. Okay? So when you assign those equilibrium equations, you will find that RA is 0.75, RB is 0.25. Okay? Now, when we have this point load at C, we need to know, or we are interested in finding the shear at C. So that one, what we will do is we will cut C and see the equilibrium equations. Okay, so now we have this unit load on top of C, okay, and then we have this support reaction, which is RA 0.75, which I've calculated from the static equilibrium. And C, this is the left-hand side of the cut, therefore downward shear is positive. Okay, so this is called VC, the shear at C, that's positive. This downward shear or downward load is positive 1, and this is upward, which is negative 0.75, and that should be equal to 0. Why? Because this piece is in equilibrium. Therefore, we get this VC. Now we have a number. VC is equals to negative 0.25 when you just simplify for VC. So that means when X equals to 2.5, my shear at that location C is negative 0.25. So we have a negative shear. So this is when I approach from A to C at C. Now there is another condition. For example, this is more specially for shear and moments, because now we are looking at a cut and in between of a member. So what happens if I look at the other half? So this is the left-hand side of the cut, the beam, right? Now this is the right-hand side of the cut, okay? If I say right-hand side of the cut, the upward shear is positive, right? That's the positive sign convention for the right-hand side of the cut. My load is at C, okay? Now, because I did not change from C, still my load is at C. What about the reaction at B? That is 0.25. That is coming from here. It remains the same. Now, if I use the equilibrium equation for this internal loading, so upward shear is positive, VC. Downward shear is negative -1. And here, this is upward shear again, plus 0.25. That is equal to 0. If you simplify this, for this VC, you will get VC equals to 0.75. So that means at X equals to 2.5 feet, my shear has a negative value. At the same time, my shear has a positive value. The reason is that as I move from A to C, my net shear is going to be negative. As soon as I pass this C, my shear is going to change to a positive value. So that's based on my static equilibrium for the representative cuts. Okay, so we have two shear values at the same location. Now my load is at C. Now I'm going further up along the beam, and then I'm going all the way up to B now. So when I reach at B, my moving load, the unit load is at B. Therefore, my reaction is going to be 1 at B end, right? B support. at A, my reaction is 0. And again, we will cut, because now still we are looking at the shear variation, or we are interested in the influence of the shear at point C, somewhere here. So to do that, we will cut it at C. Okay, and we will now consider the right hand side of the cut. You could actually consider the left hand side as well, but to be more clear, I'm taking the right hand side of the cut. So at now, we have the unit load applied on B now, okay, downwards. The RB value is 1, coming from the equilibrium or static equilibrium. And over here, since this is the right hand side of the cut, my shear is going upward, right? So this is upward, shear is positive. So we have VC going up, RB or 1 going up, another positive one, and the applied moving load at B is going down, so -1, that is equal to 0. So my net shear at C when the moving load is on top of B is going to be 0. In other words, when X equals to 10, my shear at C is going to be 0. So we have all the points that we are interested, or interested in the influence of the shear at C. So everything is at C. So we can tabulate all the data like this. So when X equals to 0, my shear at C is 0. When X equals to 2.5, these are in feet, okay. At 2.5, my shear at C is going to be minus 0.25. When X equals to again 2.5, I have a positive shear. And when X equals to 10 feet, my shear comes back to 0. So if we plot them, it would be something like this. So it comes from 0 minus 0.25 and then suddenly changes to 0.75 and drops back down to 0. So this is called the influence line, or the shear influence line for point C. In a different way, interpreting this one, if I move my unit load from A to B, this is how my shear at C is going to change, or this is how my shear at C is going to vary. What if I'm moving 10 kips of force? Everything is multiplied by 10. It's very, very straightforward, very easy, right? So for example, if I want to see, let's say I want to see what is the maximum shear of this location when I move a concentrated load of 10 kips. So the maximum is giving me, this is not the maximum, because even though we get the magnitude, this is 0.25, this will give you the higher magnitude, right? So this will be the influence, 0.75. If I run from A to B a 10 kips of force, then my maximum shear at C will be 7.5. We will do one example. I'm just trying to establish how we construct these influence lines for 3 different action types. Okay, just keep that in mind. If I move higher order of load, then it will be multiplied by that number. Okay, so now let's look at the moment influence line. So the moment, again, same beam, same load, unit load. I'm moving from A to B, same length, and we are interested in at C, how the moment is going to change when I move the unit load from A to B. And again, this is using the tabular method. Okay, now let's look at this beam. Okay, supported at A, supported at B. Using the tabular method, it's saying that you place your unit load at different locations. Okay, this is my first location that I can think of. So when my unit load is at A, the reaction is going to be the same number because it's on top of that. And RB is going to be 0 to maintain the equilibrium. Now we are looking at the moment at this section, which is at C. So what I'm going to do is I'm going to cut at C and see the equilibrium. So in this member, right, this is the left-hand side of the cut, and we have a moment going positive direction or counterclockwise because this is the left-hand side cut. And this is my reaction, RA. This is the applied load as a unit load, right? And then I will consider the equilibrium for this AC member. Since this is in the positive direction, I have MC as positive MC plus, I'm taking the moments here, okay? Plus 1 times 2.5. So from here to here, the length is 2.5, right? So this is plus, that is this moment. So this applied load makes a counterclockwise moment or positive moment about C. So the load is 1, distance from C to A is 2.5. So the moment is 1 times 2.5. And we have the reaction. So this is rotating clockwise direction, right? Therefore, I have a negative sign. This is against the positive sign convention. That's why I have a negative. So the load is 1 kilonewton, or maybe 1 unit load, times the distance will be the same, 2.5. In that, the whole thing should add up to 0 because AC member is in equilibrium. By simplifying this, I get to know that MC is equal to 0. So therefore, at x equals to 0, the moment at C is 0. So now what I'm going to do is I'm going to move my unit load from A to C. Earlier I had my unit load here, placed here, and now I'm going to move this unit load over here. So now what? I need to consider the reactions because I changed my location of the load. Therefore, my support reaction is going to change based on the dimensions here. This is 2.5, 7.5. We have these reactions, okay? And then we cut at this location and see the equilibrium here. So now my unit load is at C, right? And then this is the support reaction. And now I'm writing the equilibrium equation at C, or the moment for C, about C. This is positive MC, negative 0.75 is the magnitude times the lever arm or the moment arm is 2.5. That is equal to 0. I do not have this into consideration because I'm taking about that point, and also this point or this load is on top of C. I do not have any moments contributed by this applied unit load. So by calculating this one, right, I get to know that, okay, my MC at MC when my load is at C is 1.875. Here, now I need to look at this one, the right-hand side of the cut. Right-hand side of the cut, the moment is positive. Applied load here, right on top of C. And here the support reaction changes from the left-hand side, right? So we have 0.25. And then I write the equilibrium equations for the moment. MC minus y minus, because this is counterclockwise, and then considering the right hand side, so 0.25 times this lever arm or the moment arm, that is 7.5. So 7.5 is coming from C to B because A to B is 10. So again, MC will be 1.875. Let's move forward. So I'm going to move this point load or the unit force, unit load at B. So let's place that one at B, and see the reactions. So now this reaction is 0, again this is 1, and we get the cut for the right hand side of the cut. Okay, so this is MC positive. Okay, this is again positive 1 times 7.5, and again 1 times 7.5 is negative. So I know that my MC is now, if you simplify, MC is equal to 0 when x equals to 10. So we have all these numbers. Then we can tabulate x distance against my moment about C. So if I plot that one, this will be the influence line variation at C when I move a unit force from A to B. Okay. Again, if we are dealing with 10 kips of load, only thing you have to do is you just multiply by 10 or whatever that magnitude you are looking for, or you're just running through. Okay, so now let's take a look at this example. So here we have a cantilever beam fixed at A. This is a free end. Length is 8 feet, right? So I'm gonna run a unit load from A to the free end. And then we need to plot the influence line for the vertical reaction at A and moment at A. Okay, so we need to construct 2 influence lines for the reaction at A and the moment at A. So now what we do is we take the beam, right, and then analyze it for the reactions. So when I have my load on top of A, my reaction is 1. What about the moment? Moment is 0, right? Because if I take the moment about this A, MA is equal to 0 because there are no other forces contributing for the moment about A. Therefore, my moment is going to be 0. My reaction is 1. So what I'm going to do is I'm going to move my unit load to the midspan. It's another special point. So now, as I move this load away from the support, now it's generating some moment because now I'm creating some lever arm or the moment arm as I move my unit load from A to elsewhere. Okay, let's say this is at midspan and the reaction at A is going to be 1 because I need to maintain the vertical equilibrium. And this is the induced moment because of the fixed support. Remember, we had 3 support reactions. So this is the moment reaction. So the moment reaction, MA, is equals to 4. How come? Because I'm at the midspan, halfway of 8, that will be 4 times 1. That will be, MA will be 4, whatever the unit, okay? So this is at x equals to the halfway, right? At x equals to, let's say, 4. So now what I do is I need to take, okay, so now I'm looking at what? The vertical reaction and the moment at A. So what we need to do is we need to get a cut somewhere at the support. Let's say this is my cut, okay? This cut is very, very small cut because I need to take the equilibrium or the internal forces at A, okay? So this is very, very small. So this is the support reaction, which is MA equals to 4, which we found from the earlier step. And this will be my internal moment, M. So M is the internal moment. MA is the support reaction due to the equilibrium. RA is the vertical reaction due to the equilibrium again. Okay? So if I write the equation for the moment for this piece, I will have M, which is the internal moment in the positive way because this is the left hand side of the cut. So M plus 4 is 0, and then my M is equals to -4. Now what happens? I'm going to move my unit load from midpoint to the free end. So my reaction at A will remain the same because I'm not changing my magnitude of the unit force that I'm traveling from A to B or A to the free end, but I will induce more moment because I'm introducing more length to the line of action of this force, right? So 1 times the span length is 8. That will be the reaction, the moment reaction at point A. And now we are considering the moment at A. So we cut at A and see the equilibrium. Again, RA is going up, MA is going counterclockwise direction, and that is my reaction. And M over here is the internal force at the cut. If I write the equation, this would be M plus 8 equals to 0. That gives me M equals to -8. Okay. So after that, we know at each location of the beam where I place my unit load, my reaction, I know the reaction is 1 here, 1 here, 1 here. Reaction has no effect on the location of the load, but there will be the change in the moment, because at x equals 0, moment is 0, x equals to halfway through, ma is equals to 4. This is sorry, this should be minus. Okay, this is the reaction for. Okay, this is the internal. Okay, this is correct. So this should be -4, and this should be -8. And since we know the data points, we will be able to get the influence line. So this diagram shows you the influence line